Hello, my friends. Hello, my RF microwave designers. Hope you're having a great time wherever you are. This is Dr. Mohamed Nezami, and I'm an independent RF contractor doing circuit designs and systems. I have posted close to 30 presentations on RF and microwave device modeling, 3D modeling and design using HFSS ANSYS design tools. And so I figured now let's start a new different concept. Today I'm going to start one of my first system design presentations using what's known as SystemVue, or what it is, the Pathwave System baseband and RF system design, simulation tools and modeling. This is from the good people at Keysight, which used to be Agilent, which used to be HP, which is a bundle of their tools, are a bundle of software tools that are used to design high frequency and microwave and circuits and systems. I remember way back when they used to be EESoft and then got bought by them, and so there's a whole progression of takeovers, acquisitions, and and many different pieces of softwares that were purchased and all bundled together in what you see today, which is the Pathwave modeling tools for RF and microwave design engineers. So today I'm going to start my first session on designing the system design of a low noise block. Okay, and what that is, basically, as you can see in here, it's nothing but a frequency down converter, okay, that takes, in this case, in this example today that I'm doing, it takes a block of KU band frequencies and takes it down, bring it down to an intermediate frequency or an IF frequency that is low enough that you could take a coax and feed it down to an indoor satellite receiver, okay? So, and that's what the system is today that I'm talking about. Basically, it's simulated as a signal that comes in from a satellite somewhere between minus 130 dBm to like could be as high as minus 70 dBm if it's from GEOS at worst case. And then we amplify it, okay, through a multi-stage low noise amplifier. And then we mix it with locally generated, precise, stabilized local oscillator signal. And then we get the sidebands and we filter the lower sideband in this case and filter it, amplify it again through multi-stages of intermediate frequency to get to this frequency range, which is 900 to, in this case, 1700. Okay, but in a lot of cases, it's already 950 to 2100, okay? So the frequency range that we're going to talk about today is basically, I'm going to design it for 3 bands, which are well known, the low and mid and high KU bands that extends from almost 11 gigahertz to almost 13 gigahertz, okay? The local oscillators are basically going to be frequency synthesizers running in the S band somewhere in the 2.5 to 2.8 gigahertz. And what I do, which is 1/4 of the LO value that we need in this case. And then we take it through a ×4 multiplier. And then we amplify and filter the precise 1/4 of the frequency and feed it into the mixer, okay, as a local oscillator signal. So let's put some theory around this, and then we come back to the design. Okay, the design starts out by basically we show the frequency response, we show the the linearity. We sweep the front end of the low noise block to see how linear it is. Where does it start compressing? We look at spectrum of CWs at various stages. We look at the frequency sweeps that checks for spuriouses and images, responses, and so forth. And then the most important, of course, which you all have been exposed to, which is the budget link throughout the whole chain, okay, that monitors the noise, overall noise figure, overall gain, conversion gain, overall carrier to noise ratio, all these parameters from starting out from the front end, the low noise amplifier in this case, and traveling down through all these components to the final IF level. So that, as you can see here, the design that I have right now has about 60 dB plus minus 3 dB gain, conversion gain. It has a noise figure of about 0.6 dB, which is super duper. It has a 1 dB input compression level at minus 43 dBm. And the desired channel, if we feed it with a minus 80 dBm in this case, we can trace out the desired signal, which is, in this case, a test signal in the midband. We get minus 22 dBm. And that's basically, if you subtract 22 from 80, that's this number here, which is the conversion gain. Okay, and then, of course, this is also like we can trace the LO levels, okay, through the path. The LO that I'm using right now is it's 13 dBm mixer. So we're going to take a look at that. So the devices we'll be using, basically, we have the CE350-512, okay. This is a California Eastern Laboratory, CEL, used to be NEC. This is a low noise device. It's a super low noise device. It's a MOSFET, okay. And the Fmin, which is the minimum noise figure at the embedded right to the device here and matched to the optimal noise figure, is about 0.3 dB, okay, which is very, very nice number. We bias this device at 10 milliamps for the drain, and then the gate, we vary the voltage. So right now it's sitting at, I think we set it up to somewhere, the gate to source voltage is somewhere that would give us 30 milliamps, which is about 0.2 volts or so, okay? Then we use also a mixer, a mimic from a gas mimic from analog devices. That's this device here, okay? Then we use the LO amplifier is also from analog devices. It's this device here, which is the HMC 3653. It's got I think a 12 dB or 14 dB gain. Okay, let's look at that. We've got from 9 to 14 gigahertz. The gain is 15 dB. Okay, the compression level is this device can put up to 15 dBm or so, 16 dBm. And then, of course, the IF filter, we use a ceramic filter from mini circuits. Okay, that's this device here, this very inexpensive device that covers the IF SATCOM, typical intermediate frequencies from 950 to 2200. And of course, the IF amplifier is this device here, okay? And this has a 24 dB of gain. It's a nice 4-terminal device that has a huge heat sink that is a ground pin on this side. I like to use that always. It's a nice device. So all of these devices were chained together to make up the this one in here. So all of these devices, we entered the model. In this case, of course, as you can see here, every element has a table that you can come in and fill, or you can import the parameters from a CSV file, okay? In this case, the three-stage amplifier in here, this is my own design. I designed this, so all the values that are entered manually in here, I cut and paste it, basically. So in this case, I only have the gain and noise figure simulated. We don't have these here right now. We just have the estimated parameters, okay? While other devices, like for instance, the mixer in here, you can see that we're using the model from the analog devices library, and that you could look at the model itself is just an Excel sheet with just saying, here's the device. It's the HMC 773A. The LO power is assumed 13 dBm, and the temperature is room temperature. And it gives us a column frequencies and the other parameters, like the conversion gain is listed down here for these frequencies. And then the IIP3, the third order intercept, the second order intercept, the 1 dB compression, okay? Now, if you don't have a model from a library, what you could do, oops, I just realized I did not share the Excel sheet, so this may not have shown. Let me go again on this. So you're gonna reference this. I apologize. So let me see if I can share this on the fly. Okay. Let's see, new share this one here. My apologies. So what I did is when we click in here to the reference info, it goes into spreadsheet, which is this is spreadsheet model, okay? And it gives you basically, it's just a text file in Excel, and it gives you all the parameter frequency vector, the converging gain vector, the third order intercept vector, second order intercept vector, and then the IP1 vector, okay? So if you don't have that, okay, if you don't have that, okay, what we could do is you could, oops. Okay, let's get back here. If you don't have a model for any of these, let's say that you had an amplifier that you didn't have the model for it. So what you could do in that case is, let's see, analog devices. Let's say, we're gonna go into RF. Analog and RF. Okay, stick this on here. Oh, okay, RF here. Let's say that I had an amplifier in here that I didn't have a model, okay? So what you could do is you could either insert these values, which are the relevant values, and in that case, they'll be the same values for all the frequencies. But if you want to make it frequency dependable, you just click this and you just basically add as many columns as you want in here and fill these values in here, or create them in an Excel sheet and then import them as a file, okay? So that's, you could do that as well. Okay, so let's get back to the design. So let's get back to some theory on this. So like I said at the beginning, my name is Dr. Mohamed Nezami. I'm an independent RF designer. I design RF and microwave circuits and systems. If you need to outsource your design, please let me know. I work with various people from regions of North America, Europe, the Middle East, and I operate at a very inexpensive rate compared to the US consultants. So please reach out to me if you have any design. I design the system, I simulate and model it, and turn in the work with your engineers or your project engineer and researchers to implement the system, turn in all the validated design at the system level, then go and do the circuits, and I do my own layout, so you get a complete package. So today, in the like I said in the beginning, I have about 30 videos done, which you can check on in my channel, YouTube channel. I have about 30 videos done on microwave and RF devices using 3D modeling tools, HFS from ANSYS. But we have wrapped up with that. There are still a few topics that I need to cover. Maybe someday I'll come back around and put videos on those. But right now, what we're going to launch into is a more of the active transceivers, transmitters, and receivers and amplifiers. Okay, so primarily transmitters, receivers, and low noise amplifiers, small signal amplifiers, and power amplifiers. So I'm gonna have a whole series on those. We're gonna start out with system level simulation and modeling tools using the Pathwave SystemVue system baseband and RF simulation tool from Keysight. All right, so today we're going to start out with the KU band SATCOM as an example, a low noise block down converter. So let's just explain a little theory in here. So what is a low noise block LNB, low noise block, and why is it called like that? We have a block of frequencies that come into the horn antenna that picks up the signal reflected off the parabola, okay? And what we do is we take that signal and establish, this signal is very weak. It's set from SATCOMs, like in this case, GEOs. It could be, same approach would be done for LEOs and MEOs and other ones as well. But the signal, let's assume that it's somewhere around between minus 130 dBm to like as high as, say, minus 70 dBm, okay? And this signal is now very weak, so we need to establish a strong enough signal to be demodulated, okay? That means we have to take these block of frequencies that are at KU band, somewhere between 10 and 13 gigahertz, and bring them down to an intermediate frequency, which is somewhere between 900 to 1,000 megahertz, and then amplify it, of course, preserve the carrier to noise ratio, and put it down, transfer it down using coaxial cable. And that's why we need to take it down to the IF intermediate frequency, because eventually it's also, it has to come down, it has to be rotated to baseband or down converted to baseband. And that's what the demodulator does, okay? Both the digital signal processing section and the RF section in the modem takes the IF and puts it at another yet intermediate frequency, or maybe it could, nowadays with the high digital samplers that could sample up to like 10 gigasamples per second, you could directly sample it and then go to the DSP and whatever it ends up being, and then it's mathematically, basically complex numbers that you can rotate to baseband and start playing around with the sample rate and bandwidths and progress signal. So basically, a low noise block is this block here, which takes the KU band and puts it down at an intermediate frequency. And in this case, I took this figure from an older book, so still uses 900 to 14. Nowadays, it's more like 900 to 2100, 2400 megahertz, okay? So, and then of course, the local oscillator that is used to down convert the signal is somewhere in the 11 gigahertz, okay? So you down convert the signal and you amplify it enough so that you get it to the modem signal. And usually these low noise block down converters, the gain usually, like these ones that you see on your direct TV dish, usually they're 60 dB gain. So you can see that it takes minus 130 dBm and puts it out with a gain of 60. So that's somewhere around minus 60 to minus 40 dBm, basically, into the demodulator, okay? And the demodulator, of course, takes it down further and then takes it into a demodulator and then into a decoder. In this case, if this is an entertainment SATCOM, KU band, it puts out final result is audio and video signals, okay? But today's LMB that I'm talking about, as an example, is more like for tactical systems and for like government communications, or for these gateways that you see on boats and ships. So it's more professional than the low cost DBS commercial TV, KU band TV down converters. As an example, you know, these LMBs are not secret. So there's tens of companies that make these low noise block down converters. As an example, I took this one here, which is commercially available, and this is the specification sheet. And just to point out to you the most important things on it is first of all, the noise figure on these is, like in this case, this product, of course, the interface is waveguide, rectangular waveguide on one side, and on the other side, it's either N-type connector or F connector, 75 ohm connector. If it is for some people use them with 75, some people use them with 50 ohm. But usually the low noise is about 0.8 dB, and that 0.8 dB noise figure includes that's the waveguide to microstrip transition, and then the low noise block down converter. And as you know, like I showed you earlier, the FET device that we have from NEC has a F-min of about 0.3 dB. So usually when you design that gets up to like 0.45, 0.5 dB of noise figure. And then once you cascade 3 stages of that, you're up in the 0.6 dB noise figure. So that leaves you with about 0.2 dB for the waveguide to microstrip transition. And that's why this transition here, the rectangular waveguide to microstrip transition inside of here, that's very critical. And I have designed LMBs, and many times we had failed to reach these kind of competitive numbers because of the transition. The transition here, and if you like that area, I have in my videos, I covered about 6 or 7 videos on designing waveguide to microstrip transitions, okay? And if you have a need for one with your company that you need to design, let me know. I could work with you on those. I have some designs that are ready to go with solid model and HFSS proven modeling that you could purchase from me. Okay, so that there, and then of course there's the synthesizer for the local oscillator. A lot of times the phase noise is critical for these high level QAM modulations. So they started to put that specification out. In the old days, they didn't really worry much. It was just a noise figure. And the overall gain, of course, like I said earlier, most of these LMBs, they're in the 60s of dBs, okay? The output compression, usually it's about plus 15 dBm. And today, my LMB example, the IF amplifier has an output saturation at that level. So that tells you that the design example that I have is an actual design that I have worked on in the past, similar to that and along the line that, and therefore it's really a true system that you can actually take it out and build it and use it. The bands usually is from 10.7 all the way to 12.7 gigahertz. And in this case, in here, this commercial device in here has 4 bands. And of course, they publish the LO frequencies. Okay, they are right here. Okay. And then the IF frequencies, of course, look at that. They have them here too. So somewhere between 952, anywhere from 2000 to 2400 to 1500 to 1700. It varies, but okay. The input waveguide is WR75. Okay, so that you would know. Okay, here's another example. Oops, let's get back. Here's another example from another manufacturer, okay? And that's this one here. Same thing, you know, they give you the input frequencies are these frequencies anywhere from 10.7 to 12.7. The LOs, corresponding LOs for all of these blocks are listed here, okay? The output IF frequency is listed also in here. The gain, again, is 65 dB, typical, minimum 55. So the one I've designed is going to be, I'm specifying it for 60 dB plus minus, I would say 2 or 3 dB, okay? And you get the flatness, of course, within, say, a 30 megahertz. That's a single transponder. The noise figure in this case is 0.8 dB, which corresponds to 59 Kelvin. If you like to, some people like to, the LMBs, they specify them not in terms of noise figure, but the temperature, effective temperature. Okay, phase noise, the image rejection is an important one. It's 40 dB in this case, rejection. Wonder if the other one didn't specify the image rejection. No, it didn't. Okay, so in my case, that's one of the parameters that we have to verify in the SystemVue system modeling. We have to make sure that we cover that. The output compression is 15, so you can see that if it's 15, then with 60 dB of gain, that means your compression input 1 dB compression point is somewhere around minus 40 dBm, and that's the same thing that I have on my system as well. So the output connector, usually these are F-type or N-type, 50 ohm or 75 ohm. Okay. So where does this LMB fits in some of the these SATCOM terminals? Usually it's right here. Okay, so we've got, this is a system that is unlike the systems that you have at your home. This is a two-way communication system, more like a VSAT. Okay, and so you have the block up converter, and like the corresponding this on the transmitter side, and then you have on the receive side, you have the low noise block down converter. Okay. And of course, you have the horn feed, okay, and then the receive signal comes in. There's an OMT, and I did cover OMT designs, so I have several various designs like those in my videos. You can refer to that. And then you have in here, because this is a high power and somehow out of band energy can leak and saturate the low noise, the super noise figure, low noise block down converter. So they put in a waveguide transmit rejection filter. Okay, so basically that's like a front end band pass filter for this. Okay, so when you look at the inside of this, this is an older generation LMB that I grabbed from the net. Okay, so it's already published. This is public domain. Basically, we have the horn antenna comes in and interfaces with circle waveguide or with a circle waveguide on the OMT, and you pick up the signal both horizontal and vertical. So in this case, this probe picks up the vertical. The horizontal is being picked up by a pin right here, and it's hidden behind this a quarter wave distance away from this here. So this signal comes in, and we go through various stages of amplification. And in this case, let's follow this because this block diagram here was derived on this. By the way, this uses a DRO. This is the dielectric resonator. These are DRO local oscillators. We don't use those. We use, nowadays, we have phase lock loop synthesizers. They're more stable and more precise in frequency, and they're more appropriate for digital communications. So let's assume still though the RF low noise block down converter is valid in this case, regardless that it has a DRO instead of a PLL local oscillator. So we have the device, we have the input signal comes in here. These are low noise, super low noise amplifiers, and from their look and knowing the radial stop on the both on the gate and on the drain, this is a NEC device, similar to the one I've used as well. So you have both the vertical and horizontal are joined here in a T-junction. And of course, when you have your telecommunication system, it's either you communicate the horizontal or the vertical, okay, not both at one time simultaneously. Some systems do, but then they would have a different LMB than this one. This one here is designed so that you can turn off either one way or the other. That's why when you sit on your TV, you need the information whether that's vertical or horizontal, so you can turn off either this transistor or that transistor, because you don't need these both biased together. You get one signal, and then here you amplify it separate, and then you have a common amplifier for both in here, then pass filter, and that's what here. So we have one amplifier here for both the vertical and horizontal, and then we come in here, there's another amplifier, which is this device in here, and then there's a band pass filter. And the design example that I'm going to show you today, I designed a hairpin filter like this one, similar topology. And then we come in here to the mixer. This is an active mixer that basically gets the RF signal. And you can see this is a two-stage amplification, okay? In my case, I use three-stage amplification, because the mixer I'm using is passive, not active. It has conversion loss, not conversion gain. In this case, they've used an active mixer, so they didn't need a third stage because it's included in the mixer itself. The mixer itself provides a gain as a third stage, okay? The local oscillator, like I said, this is a dual frequency. So also in this case, they either run this frequency or this frequency. So you have a microstrip resonator in here, and you have the dielectric resonator sits in here. And so this whole thing is a DRO, okay, with this active device in here. The signal comes in and gets coupled to the drain of this FET, which mixes in here, which causes the mixing. And then, of course, you have an IF filter in here that rejects the LOs in here. That's mainly because you really want to reject those LOs. Also, the LO, you want to make sure it doesn't bounce back and gets transmitted from the antenna back to the satellite. That's dangerous. So that's why these devices in here, we want very high isolation, okay? So, and then if we go, the IF amplifier is also two stages in here. As you can see, here's one amplifier, here's another amplifier. So we amplify them and then go into the IF. The DC for this, because the LMB sits up at the mass of the ground station. So we have the DC is also provided. We don't have, you never see a plug for power on an LMB. So that's because the DC is always sent up in the IF cable to the LMB. That's what you see in here. Basically, this is a printed choke inductor that chokes out the RF, so it doesn't impact the IF and this frequency. So, and then we come in here. This is a voltage regulator, as you can see here, 7805. That's the 5-volt regulator. And then from that, we generate a whole set of biasing. Okay, this biasing goes to the various drains and gates. So we have to create negative voltage in here and send to the gates of all of these devices, okay? Then we have this device in here. This is usually this is for controlling. We have the DISIC that tells this LMB whether to go vertical or horizontal, and that's basically switched with all this stuff in here. I don't want to go through that. That's beyond the scope of what we're talking today. Here's another example that shows it more clearly. This is a single polarization example where this is the solder bulb in here. That's a metallic pin that is inserted into the waveguide. Okay, so and then we get this has a 3 stages of also LMB low noise amplifiers, similar to the one that I am going to present today that I designed. They have in this case, they don't have a hairpin filter. They have an edge couple filter, okay, which is a little different, but same thing. This one usually takes larger space, as you can see here. And then, of course, you have the mixer in this case. There's this quadrature pattern here that creates, basically brings in the LO, and you have dual diode in here that you mix as a mixer. And then this is the IF amplification stage. Of course, like I said before, the DC comes in here. Here's DC regulation. Okay. Here on this one here, you don't have any DROs. This is a phase lock loop local oscillator. Basically, it's made of. This is the TCXO. This is the crystal, the temperature compensated crystal oscillator that feeds in a PLL chip that basically with an oscillator in here, a VCO, and then the VCO gets filtered again through an edge coupled device, and then amplified the level, and then go through the quadrature point to the mixer. Okay, and you can see there's an open stop right here. See that open stop here? That's to reject the LO signal. If you take that, that's actually open stop at the LO frequency. So you can measure that and know exactly what the frequency of the LO in this case. Okay, so let's get to the design that I have, which is basically, that's what I'm going to present today. So we have this design in here, which is basically, like, again, I said, this is a multi-stage, 3-stage low noise amplifier in this case, okay? And then there's the mixing in here. There's the LO presented in here. I'm not covering today the phase lock loop, local oscillator. Hello, my friends. My apologies. I have to, I just realized while recording the first session that I stopped sharing the SystemVue, the Keysight SystemVue window. So I'm going to insert this in. So you're going to see a sudden change of concept. So I apologize. So this is the design again of the low noise block down converter. First of all, I have a signal in here fed, which is at minus 18 dBm at one of the center frequencies, okay? And then in here is basically my low noise amplifier, okay? This is the data in here was inserted from the low noise amplifier design, mainly the gain, the noise figure. Okay, and then of course we have the front end filter, which is a printed filter. So let's look at the LNA first. Okay, we have LNA. This is a printed filter, and then we have the IF stage in here. We have the mixer in here, and then we have the IF stages of 2 amplifiers and 2 the ceramic filters. These are the 2 ceramic filters, and these 2 filters, of course, are from many circuits. They're surface mount filters. The LO, I'm assuming that the signal, the synthesizers are right here, 0 dBm. So I take that and then multiply at 1/4 of the LO frequency that is required. Okay, so I multiply that 4 times, pad it, and then amplify and then filter to go into here. The LO filter that is here is also printed. So let's show you that again in here. So let's start showing the first one is the front end filter. Okay, so the front end filter is really this. Okay, it's a printed filter. Okay, 7th order, and the design is basically a hairpin filter. Now This filter, as you might know, right now needs more work because this has to be passed on to an EM 3D modeling to make sure that this filter is centered correctly and everything is fine, okay? The frequency response is this, okay? So it passes the front end signal. What you see the different coloring in here because this was synthesized with Genesis. So these are the areas for the in-band return loss and insertion loss and the out-of-band rejection, okay, both up and down. So that's what these are for. These were used as a way to optimize the sections of these filter. The other filter is the LO filter, okay, and that filter basically is this. So it's a smaller order filter because all we need is just to reject the harmonics of the filter. The filter is shown here. This is the band filter, and again, this was optimized as well. Okay. Then the low noise amplifier is basically was designed also using Genesis. Okay, we could have designed this with ADS and use the harmonic simulator to do large signal analysis as well, but we didn't need to that at this time. So I'm using this NEC device, the CE3512, okay? It's I'm biasing it right now at 2 volts drain, and the drain current is 10 milliamps, okay? And I'll show you in a minute, the gate voltage is assumed to be also minus 0.2, I think. So it's a 3 identical stages. Basically, we have stage 1, which is this here. Okay, so this is one single stage. Okay, that is copied twice. Okay, and basically we've got the gate biasing. The right here. This is the network for bypassing the DC. This line here is a quarter wavelength line, and this is an open quarter wavelength radial stub. What this does basically, this is to provide short at this point. As you know, this is a quarter wavelength. A quarter wavelength, if it's shorted at its output, that means it will look like open at this point here, and that's what we want. We want it to. It's a DC insertion mechanism, so we want the DC to come in here. These components in here are just to bypass the DC noise. Okay, so we want the negative voltage to come in here and get in here, and this amplifier in here doesn't see any response or any loading by the DC insertion. Okay, same thing is done on the drain as well, same exact network. Okay, so that's what this is. The performance of this, like I showed you earlier, I think the gain was about 37 dB in here in band. It does, however, roll off a little bit toward the end at 34. So we've got about 3.5 dB roll off, and it will show in the overall design. And I think that's what causes it. If you look at the LNA single device itself, is very flat. This is the gain, unmatched gain, okay, the available gain. And the noise figure, of course, is right here. So we're down at 0.542, worst case, okay, or the best case in here. And then at the edge, it runs to like 0.62, okay? And so if you look back on the overall performance of this, as you can see here, the roll off is clearly shown in here. You can see it. So it's got about, and so we need to do further work on the LNA as well. So that's what this is. The design, basically, we start out, if you look at the design from the beginning, let's look back in here. So the simulator, the tool, let us define paths. One path I'm defining, I have about 5 paths. Let's look at them again. Okay, so I have about 5 paths right now. No, actually 6. Okay, so we've got 6 paths. These paths, basically, I define them, some that are associated with this path here from RF to IF, and some with the LO from the synthesizer to the mixer, okay? And the reason I do this is because I want to track the RF level of the LO just to make sure that this mixer gets what it requires, which is about 13 dBm. That's what the manufacturer said. So if we go back to the devices, so let's look at the mixer. Now this mixer, it needs, it's a, basically it needs a 13 dBm level. So if you look at the response here, it needs about the LO level is specified at 13 dBm for all the modes that it operates in. Now, the LNA device, as I was talking earlier, is biased. This is the device, and you can see the noise figure is 0.3 dB, which is superb, and the variable gain is 13.7. Now the drain bias, the gate bias is biased right now. If I biased it at 10 milliamp, that means my gate voltage is at somewhere around a half volt, negative 0.5 volt, 10 milliamps, okay? And so the drain current 10 milliamps, that means you can actually, that's where the bottom of the board, that's why 10 milliamps was picked, because it's very low noise point at that point. You get the 0.3 dB of available noise from the device. Okay, the filters that I mentioned earlier, one of those filters is this filter. This is the ceramic filter from Mini Circuits, okay, and it's got this response in here, which is very good and very inexpensive filter, okay? So it does have 40 dB of rejection outside the SATCOM band, which is sufficient, okay? So let's get back in here. So now if you look at this path here, we can look, the one thing that we could see here is the budget link calculations on here. And so the first thing we want to look at is the final point in here is if you look at this here, it shows the progression. This is the block diagram of the LMB in here. And these are 4 curves that represents the accumulated gain, the accumulated noise figure, the input 1 dB compression point, and the desired channel power in dBm, okay? And in this case, I could see that the overall gain is 57.8 dB or 58 dBs, I must say. The noise figure is 0.59 dB, okay? The input compression point, 1 dB compression point, is negative 42 dBamps, okay? That's really well. So that means the system will be fine because the SATCOM signal varies between, say, minus 130 dBm to minus 80 dBm, and very unlikely that you're going to get, unless you get interference of some sort, you won't get to be with an input level that reaches that high. The desired channel in this case, if I start out minus 80 dBm in here at this curve, basically I end up with minus negative 22 dBms, okay, which is pretty good for a down converter. That goes into the modem, and it's within your typical modem signals. Now, the modem signal takes this, and again, it amplifies it and down converts it again and processes it further. So one thing to notice in here, why this tool is powerful and important, because I could come in for the noise figure, for instance. I start out with a noise figure out here at a 0.49 dBm when it's finished, right, at the device in here. This device in here, let me go back to that LNA. This device in here, I'm assuming the noise figure is about 0.54 dB, okay? That's the 3 stages of LNA, which is this. All of this right now, all of this LNA is lumped into a single unit model in here. That's this device here. See this device in here? If you look at the model for this device, this is basically what I list. I list the noise figure and gain from that particular simulation. So this represents the actual circuit implementation of the LNA, okay? Now, the thing that you notice now, I don't want to, it's beyond the scope of this presentation to talk about the theoretical calculation of the link budget, link parameters. The overall gain is easy, okay? It's just a summation of linear gains on all of these devices cascaded together. The noise figure is always going to be, of course, you know from the equation of the noise figure, it's the noise figure of this device here. And assuming, since we have very high gain, we have about 35 dB in here, 37 dB in here, and we have the rest in here, like 50 dB. So it's almost the noise figure is really of this plus a tiny contribution from the rest of this, okay? And now, so the thing that we want to watch is you look at the, the good thing about this tool is you can actually come in and look at the progression of gains and losses and try to analyze and see what stage you can do an improvement. For instance, you know, we start out with the noise figure being at 0.49 dB, and then we start out anterior, and then we jump up a little bit due to the mixer, okay? And then we start jumping again and again until we get to one of the IF amplifiers, okay? That's where you're at the input of that device, the noise figure is 0.542, and the output is 0.589, okay? Of course, that's not a whole lot of numbers because right now this curve here is fooling because this scale on the right is for the noise figure. So let me go back and fix that so that, let's say, for instance, that we wanted from 0 to say 1 dB, okay? And now it's much better now, but you still see the jump in here, okay? So that jump is due to this guy. And why is that? Is because if you go to this device, the that device data sheet, okay? Or let's look at the, okay, let's look at the device data sheet. So that device is this device here, and this device here, the noise figure is specified to be 2.9 dB. So it's got a 3 dB noise figure. And the reason for that is because this device here has an output compression point of 15 dBm. We want it to stand high level signals so that it doesn't have, and that is basically is a trade-off. So you could replace this device here. If you look, let's look again on the data for the model on this device. So you look at the noise figure, it's 3 dB and 4 dB in some frequencies, but down in the L-band section or the IF frequency location, it's about 3 dB. So we could improve the noise figure by 1/10 of a dB, but again, we may fail the compression, okay? We need the compression, the output compression point. Let me see if I can add that into here. Okay, so that one. The output. We have the output saturation, okay, the input, okay, 1 dB, okay, here it is. Okay, so let's add this guy in here. Okay, where did he end up? He ended up this one here. So that's, let's get rid of this. Let's look at again at that. So we've got 14.2 dBm. That's this curve in here. So we can see that in here, this jump in the output compression point is good, because that's what we need. If we want to reduce the noise figure further, we're not going to end up with a response like this. So that this is good. So the design is cool. Okay. What else we wanted to talk that I missed in that discussion? I do apologize. I mistakenly clicked the unshare window for this. So this video, you won't see it on there. The other thing I wanted to share with you was okay, now I recall, is if you have these devices, let's say that if you didn't have a model for them, you could create the model yourself. You could come in here and either fill in these values in here, okay? You could come in and fill these values, but if you fill them with a single value, that will be particular for all the frequencies will be the same. But if you wanted frequency dependent, so you add these and you start filling all these parameters in here, or you import a CSV file that contains these ones. So what you do usually is I would copy the you export this, for instance, and then you could look at the part of those. All right, so that's it. Well, thank you very much. Let's continue. Okay, the other thing I wanted to show basically is how do you verify more the performance of this chain. We did go through the linear response of the various stages as far as the overall noise figure, overall gain, overall output and input compression points, and noise figure. We needed to look at the basically the LO paths, and the LO path. One of the things we want to make sure of is the fact that the mixer is going to get sufficient LO drive level. This mixer in here, of course, is specified as a 13 dBm mixer. So we needed to make sure that the LO level is plus 13 dBm at this point. The synthesizers, which we do not cover right now here, is assumed to have 0 dBm. Okay, so we end up with a multiplier chip. That's the other thing. I don't think... okay, I didn't show you the data sheet for the multiplier chip. But the multiplier chip is basically the HMC 443. Okay. I don't have the data sheet right now for it, but we'll come back to it. So when we look at that path from here to here, that path, we have to define a path to it, which let me show you. So we have the paths are defined. I have like 6 paths in here defined. And one of those paths is for this path here. This one actually traces the path from the mid to the multi-source, okay? So what I'm doing is I'm trying to look at this here, from here all the way back to here, okay? And that's critical because that shows you the LO feed through, and it shows you the LO level at these various points. So when we look at that, so you can see that the LO level at that point is 12.361. So it's just a little bit, but the mixer specified plus minus 2 dBm. So we're still within that range. And you can see, of course, the how the signal progresses. You know, you start out with 0 dBm, and we go out, we pad, and then we have the N times multiplier, which has a little gain. The output is specified at 7 dBm, plus 7 dBm. And then we pad again, and then we amplify in the LO amplifier in here. And then we have a little, the filter in here has a little tiny loss. And then we come down with a pad that is inserted to assure the reflection loss is well maintained here. That's another thing we didn't talk about. The fact that in the design in here, when you look at this, the mixer is surrounded at all these inputs, the RF input, the IF output, and the LO input is all has 3 dB or even 4 dB in this case. Well, actually, this one here needs to be 3. That's why the LO dropped a little bit. So let me rerun this again. So I'll show you that back. But what we have basically is these pads in here are important because we need to make sure that the mixer outputs, these are diode or active fit mixing mechanism. We need to make sure that there are no reflections back and forth between all these ports, because as you know, if the signal goes in here, reflects back, it's going to remix again, and it's going to reflect, it's going to leak out this way and not be absorbed. So we need to make sure that all of these are absorbed well. Okay. So while we're still waiting for this to run, let's look at other things as well here. Let's see. We can see the low levels, the IF signal. We can see the spectrums of these CW signals. Okay, so let's go back and check this path, and there you go. See, we recovered the 1 dBm that we lost here. Just realize that the pad on the mixer LO side was set to 4 dBs instead of 3. So you can see how powerful this tool is. So we have this design now. Of course, the only piece that is really designed is this piece in here, the 3 stages of LNA. Now we need to go, where do we go from here? Well, one of the issues that we have to do, we have 2 filters that need to be EM'd. We have the RF filter and the LO filter. Okay, so we've got this filter here, okay, and so this filter here, this is the layout for the artwork for it, synthesized. We need to take this and 3M it. The same thing we have to do for the other filter as well, the LO filter. Now that's one thing. So we need to take these into either RF Pro in Pathwave ADS, or we take it into HFSS, reconstruct the stack layer for the material. And I believe this material was Rogers, like I said, 6004. Actually, we can see it right here. Hold on. It's defined in the filter section. So, oh, it's Roger 4003. So this is the substrate. Okay. And then we start going into the data sheets for all these various parts and draw the schematics in a schematic package like Allegro, or CAD or Mentor Graphics or Altium, and then do the layout. Okay, once the layout is done, we have to go back again now and perform what we call post-layout verification, which is we have to EM all these pieces and do co-simulations. We have to take all these pieces, chop these, cookie cut the board into pieces and verify using the EM in conjunction with S parameters of these devices that you're using, that the overall is working. And then you give the green light to the layout to go ahead and spin the board, send it to assembly, and so. Now, one of the things that we need to talk about is how do we verify the spurs and harmonics, and that's where we have what we have is the we swept the front end of the system, and that's one of the ways, the powerful methods in this package is that you could come in and actually sweep the front end and see what signals do you get in. Of course, if we sweep it from DC to say, I think, let's just, from DC to like 40 gigahertz and see it's really mathematics right now because a lot of these really can't propagate even in that board. But what it will give you power at various locations where the signal, where you can see something happens, interactions. Like this peak in here, for instance, that's our desired signal. We have our IF signal in here with the roll-off, 4 dB roll-off that we have an issue with, which we will fix later. We have to go back to the LNA and fix that. We have a DC level value. Obviously, we don't have any capacitors in the system, so we did catch that. And then we have all of these various components. Among them is the image, okay? And then now the good thing about this tool is you can hover over any of these spectral components and find out what exactly they are. Like in this case, it shows you this is, let's put a balloon on this. So we can create a balloon on this. And we can come in here and we see that this is at these frequencies, at this power level, and this is happening from twice the difference of the 4 times the LO synthesizer. So that's the LO value. We subtract the LO from the front end signal, the SATCOM signal, and then twice that. So that's the second harmonic of the RF, the IF. So that's why these LMBs usually chop them to bands, is because of this issue. So that in this case, this I would use up to this frequency only. What that frequency, of course, let me just click out this so we can manage to see it better. That's about a gigahertz, okay, or say 1200 megahertz. So, and then the second band, I would switch in the second oscillator, end up and move the second harmonic further. But even though this is at minus 80 dBm and you're 20 dBm, that's 60 dB below your desired signal. So it's not even shown. It's not significant. You've got other things in there as well coming. So you can go, you got some CWs in here. These dots are CWs, and they're due to the LO interaction with itself or with the IF. Well, the input signal is CW at this moment. So that's a specific single frequency interference of some sort, a spur that you can, but all of these, you can see that if I come in here and say, don't show me anything, say below, I would say 70 dBm, okay? You can see that I don't see anything except one single spur, which is this one here. Let's create a balloon on it. Okay. Create balloon. Okay, so, well, that needs little digging. So there's a whole further of stuff. So you can see that how powerful this tool is. Now, let's see what else we need to show. We did show the, okay. Of course, we did show the power sweep of the front end. This is where we sweep the front end from minus 80 dBm to minus 30 dBm, and then watch the output. And of course, the output saturates at 15 dBm, which is what we want at 40, I would say 47 dBm input level, okay? And then, of course, this is the frequency sweep of the front end. So we have this frequency to this frequency. Now, this here is the image, of course. You've got the lower sideband, the upper sideband. So we need to make sure that this is way down, and it is way down. It's more than 85 dBm below the, well, it's absolute power. So it's minus 85 dBm, which is from 25 is like below 60 dBc. So this is good. All right, so that's about it. Let's continue. Oscillator, I'm just assuming that I'm getting 0 dBm from the local oscillators at 1/4 of the LO, okay? So we have this design, and then I'm going to show you the basically the let's see, the front end filter, okay? That's the front end filter, so that's the layout for it, and that's the schematics for it. That's the schematics, okay? And this is the layout. This was synthesized in Genesis, okay? And then I have the LO filter is a lower order filter. You can see right here, just the 3 sections, okay? And that's the schematics for it, okay? So that's the LO. And then I have the low noise amplifier, and that's basically this here. And so I'm using the FET, the NEC FET, okay, at 10 milliamps in this case, 10 milliamps, 2 volts drain volts. And the gate, I believe it was the gate and drain. This is the, so these are 3 stages, okay, but they're identical, okay? So I designed one. Let's look at just one, which is this stage here, okay? So we have the device in here. We have 2 vias on the device that we're modeling here. And then we have a microstrip network that basically the input matching, the output matching, and then the biasing on the drain with the bypassing in here, okay? And the same thing on the gate as well, okay? And of course, this was done passively, so we're not doing large signal design. This is small signal based on small signal S parameter file for using the S parameter file for the FET device, okay? So there's a radial stop in here that basically helps put this point here at short so that the quarter wave line in here looks open from an RF point of view, okay? And the performance of this I have captured in here. So this is the gain, and you can see the gain is about 37 dB. It has an issue right now, the gain roll off, and so we've got 34, and here's 37. So we've got about 3 dB or more than 3 dB, 3.5 dB of roll off toward the end. And that's causing an issue there. So I have to revisit this and redesign it a little bit, tweak it more. So this line in here shows the F-min for the device. Okay, this is from the manufacturer. And this one in here shows the noise figure of the actual design, the overall design, the 3 stages. So we've got gain of 37 dB, and then the noise figure is close to, as you can see here, it's not even 0.6. It's about, in the mid band, it's 0.54 dB, which is very good. So now took these 3 stages and of course, put that model into the front end right here, okay? So if you look at these frequencies in here, got the noise figure, got the gain at all these frequencies, okay? All the way to get to the 0.54 at the KU band, okay? So let's get back to the theory again, and then we'll come back to the simulations. So when you look at an LMB now, of course, the frequency allocations, why you chose the IF at this particular frequency, if you're designing this in general from scratch and you have the luxury of choosing an IF, in this case, I did not have that luxury. This is dictated. We have to have an IF 950 to 2400 or 1700. So in this case, I did not have to perform what we call IF, or that's basically the study of trying to find a clean spot to pick as a intermediate frequency. Because as you know, when you mix in harmonics of the received signal with M order harmonics of the local oscillator and their corresponding spurs, of course, and harmonics, all of this comes up, it's predictable. And so there are tables that you can actually either measure, like the people that sell you the mixer, they give you these values. Okay, so for instance, let's go back to the PDF files. And let's check out let's look at the mixer. If you look at this mixer in here, okay, toward the end, they give you all these values, of course, and you can build your model using this. And that's what I did. Whenever I have a device that I don't have a model for, is you come into here and you can digitize these by hand. So you can put in an array in your Excel sheet from 8 to 24, and then you put the conversion gain is this much. You read it out by hand, by eye, ballpark it. Or you could, there are software packages that you could actually give it this diagram and they digitize it. You give it the limits, you give it this, the spacing, and it actually comes up and gives you, spits out an array of numbers. And you can use that in your Excel sheet if you want to go to that extent. But this mixer in here, usually they give you these. These are the specifications for the spurious performance. And what there is, it's all the components that they give you. If you have an IF frequency this much, then this here, which is the M times the RF frequency minus plus N times the LO. This is when you have minus, or in some cases you have positive, which means that this is actually the down conversion or the up conversion. Okay, so let's see if you have up. Let's go here. Okay. So you could either specify it's minus or positive by saying, is it a down converter or up converter? But they give you these tables. So they give you these tables where you have M times the RF frequency and N times the low frequency. And the N and M are numbers between 0 and whatever numbers you want to go as high as possible. But you don't want to go so high, because at that number, these are the dBs, of course, relative to the desired signal. You can see that it's like, say, it starts to go down, way down, that it would not matter. So in this case, in here, these are in the 70s, maybe the 40s, of course, important. But when you get to these levels at minus 90 dB C, that's, you can't see that even. So these here, you can put them, there's ways to put them in your model, in the mixer model in here, so that you can incorporate these, okay? Now, we were talking, let's get back to this here. So again, so if you're designing this in general, you would want to run this type of spurious analysis, okay, and pick the IF in the area where it won't be clean. All the IF spectrum from DC to light will have some spurs and harmonics, but you want to locate a window somewhere where the signal, the resulting signal from the NRF and the MLOs and the whatever leaks in there is actually way down below the level, say minus 60 dBc or minus 80 dBc, so that it doesn't cause any interference. Now, the other issue is the gain distribution. How am I going to distribute the gain? In this case, I was lucky because this example, we have the people that manufacture these amplifier LMBs. So we know exactly all of them have picked. They allocate 30 dB in the front, and then the IF 40 dB. So that's 70 dBs. And then 10 dB loss is assumed for all various stages of the, you've got passive mixer, which has usually about anywhere from 6 to 10 dB loss. And then you have, I have, in my case, I have these pads, these attenuators that are thrown in, and these are at the IF frequencies. They're just a T or pi network of resistors, just 3 resistors, okay, surface mount resistors. But in this case, at the KU band, they're actually more packaged attenuators, okay, from I think Smith Interconnect makes some, Mini Circuits makes some, okay, and they're small, tiny packages that you use. So we use these to anywhere where we want to make sure that we have a good return loss, so that the signal is absorbed instead of being reflected. For instance, one critical area is this mixer in here. We don't want any signals bouncing back and remixing again and going in and reflecting back and remixing again, and it becomes very hairy. So why not put these pads in here so that we are sure that we have decent return loss. Same way in here, of course, all the external ports. Of course, we don't put these anywhere where we are trying to preserve the noise figure. Like in this case, I wouldn't put this in here in the SATCOM weak signal path in here. You wouldn't want any losses, and it's beyond the scope of to cover what the noise figure equations. I'm assuming that you know those already. So any loss you put on the front end here is basically gets added directly to the noise figure of the LNA. Okay, and the LNA in this case in here, like I showed you, the manufacturer makes this device with F minus 0.3 dB noise figure. When we built it in 3 stages, I got it up to like 0.56, 0.6 dB. And again, now we have, in this case, we have a loss in here, which is the rectangular waveguide to microstrip transition, which I allow only 0.2 dB of transition loss. And that's what I'm hoping, of course. And that's usually designed by another person and who is more geared toward microwave assemblies. And usually in my past experience, that's where the most critical point, because I designed this for 50 ohm input and it comes out nice and neat. And then as soon as you attach the transition to it, your noise figure go up to like say 1.5 dB, which you'd be very upset. Okay, so again, in my case, the gain distribution here, we saw that 37 dB in here we got. Okay, and in these 2 devices in here, these 2 devices each has, I think, 24 dB of gain each one. So, but there is a bunch of losses, so that all that adds up. Okay. Now the filter, the front end filter is printed filter, and in this case, I picked up the hairpin filter. This is synthesized with Genesis, as you can see from the different coloring in here. These are the areas where I specified the for the optimizer. The optimizer, you synthesize it and then you run the optimization on it. So you can actually, like in this case, for instance, this block here is for the in-band return loss and insertion loss. And these are here for the rejection bands, both the upper and the lower. Now this here, the story is not done yet. So this one here, we need to perform EM simulations on it. So we export the DXF or the Gerber file of this from Genesis or from ADS Momentum, if you designed it with that, into RF Pro or into HFSS, and we attach ports. We reconstruct the substrate, and in this case, this was done on 4003, as I recall. And then again, you have to recheck this with a true 3D EM simulator, okay? The LO, likewise, the LO filter is a simpler filter, and the objective of this LO filter was to reject, because we're coming in the synthesizer, to build the synthesizer at KU band, that's a lot of work and it's very expensive. So we run our synthesizer at S band, and then we have at 1/4 of the frequency, and then we have a multiplier 4 times, which we need now to filter the components that comes out of it and preserve and contain pass only the true LO the devices, and that's what why we use this. But it's a loose filters because essentially we just need it to, like, say 30 dB below the main LO signals, and usually that works. Okay, so these are both filters, okay, overlap together just to show. And as you can see, the shape, the skirt is ideal because it's calculated really. It's not EM'd, okay? So as soon as you run this into an EM, it's a whole different ball. The IF filter is basically from many circuits, and it's the ceramic piece. It's very inexpensive, so I use 2 of those, and it's very nice and comes in, and you just basically make sure you don't mismatch it. Other than that, you get exactly what the good people over there have used. The 3 stages, 1 stage, 2 stage, 3 stages of LNA. Okay, in the front end, this is the response. Like I told you, there's a roll-off in here that needs to be fixed, and that I have to go back and rerun this again, optimize it. Okay, the overall, this graph here is what we call the budget link calculations. And what the system does is you have your system blocks down here, okay? These here are basically the path in here. So you specify the path. Let me just show you. Let's go back to the simulator. See, when I run, this is, so what I want to do in this case, I want to run an RF path analysis that analyzes the signal from the SATCOM input to the IF and also from the LO all the way to here. So you go to your RF simulation and you go to paths and you have to specify the paths, okay? And these paths right now, all these paths, we have path 1 to 5, they basically evolve around specifying the input and output and what kind of analysis do we want, okay? And that's basically what those are. So one of the paths that I did is you want to analyze from here all the way to here and then show, and another one from here to here. The reason for this is because I want to see, make sure that the LO at the mixer is 13 dBm, because this mixer is a 13 dBm mixer, okay? So let's get back. So now this nice tool from SystemVue, it shows you the basically the okay. So it shows you the signals. I picked, in this case, I picked show me the noise figure, okay, which is the blue one in here, which is on the right hand side, and show me the desired signal, okay, which is this one in here, and the 1 dB compression point and the overall gain. So you come in here and can trace through the chain, the progression, the accumulation of all these parameters. Like you, for instance, look at the noise figure. You start out with way down here, say at 0.3 dB of noise figure or 0.4 some noise figure. And then you start increasing the noise figure until you get, of course, right here to these here, all the way until you get to the final value, which is 0.59. So these are nice tools because you can see where the system actually, the noise figure has increased, okay? So for instance, this jump in here from 0.54 to 0.6 is due to the noise figure of the IF, the first IF amplifier. And that's, of course, in this case, you could have worked the fact that you could bring it down a little bit. Or for instance, you could even back here at the mixer output, right at that point in here, or at this point, you could have made it go like this, but these are only 0.2 of a dB, which is very critical. But in that case, we are limited by the fact that we needed a resistive absorber at the mixer output, okay? And then we needed these devices from an economical point of view, even though this device here, I believe the noise figure of the IF devices was somewhere, I think it's 3 dB. Let's check into that. Let's see what that is. So we've got this device in here. The noise figure is, this device is 3 dB, okay? This is the IF device. You could replace that with a lower noise figure device, but of course, in that case, that might be too expensive, and you also might run into the fact that you won't meet the linearity, the compression linearity, because as you know, it's either you have a linear front end that the 1 dB compression point is higher, or you have lower noise figure. You can't have both at the same time. So that's probably in this device why I picked that, okay? All right, so what that gives you, it's a good analysis tool because you can find out, you can optimize your chain and make sure that all the various parameters, and so this is your final Now, this one here sweeps the front end and shows you the output power, okay? And you can see the right now, the front end from 11 to 12 gigahertz, okay? And of course, you can see the slope right now. Oh. The slope right here is due to the LNA, and I'll show you in a minute in the simulator that it's really due to that. So this is the desired IF frequency, and this, what you see in here, that's one of the parameters that we want to make sure that we are below 40 dB. As you can recall, the image rejection was specified to be at minus 40 dBc, okay? And this is well met, okay, right here. So you can see that right here. The compression curve that shows you basically you sweep the front end desired signal from minus 80 dBm to minus 30 dBm, and you measure the output, and you can see right here it's linear all the way up to when you get to the 40 dBm or so, the 47 dBm starts compressing, and then it saturates at 15 dBm. And that's coincidentally, that's the number we showed earlier. That was the spec on the one of the commercial LMBs that we saw. So the IF device, you have to pick this number here so to fulfill that, because really you want the device not to start compressing when you have a strong satellite system. Otherwise, the quality of the reception gets bad. The other path that I'm looking at is the progression of the LO signal from the PLL loop all the way to the mixer. And so in this case, you can see right here, it was 13.3 dBm. It's at the input of the mixer right here, okay? And that's what we want. We want the LO to see 13 dBm. That assures that that value is met, okay? This is what we call a front-end sweep. We put in a certain level of a signal, and then we sweep the front end, and then we watch what signals comes out. And in this case, you can see here is the desired signal. We have DC because we don't have any capacitors to block the DC values from the mixer. So we have DC in here. And then we have the desired IF signal. And then we have components at this level, minus 90 dBm. They're way at minus 100 dBm. You see that? So they're really 70 dB down from the desired signal. So even though they are in band, some of them, but we don't care because they're way down. Now, if we increase the signal to minus 80 dBm, that gets higher, and you start seeing other things comes up, okay? Like in this case, this here and this here. And I'll show you in a minute, these you can identify, okay? That's the good thing about the SystemVue tools is you can look in here, hover on this, and it actually tells you mathematically what has caused these products to come here. And then you can go back and find out what it is and then filter. Like say, for instance, if say the IF interaction, nonlinear interaction in the mixer between the input signal and say the seventh harmonic of the LO has caused this to fold back in here, then obviously you need to go back to your filter and make sure that your filter on the LO does not just band past the closing signals, but out here it doesn't come back and becomes all pass at the that particular harmonic. So, and this is what I was talking about. So you can hover to these, and it will tell you, for instance, in this case, this one here was caused by twice the multi-source signal, which is my SATCOM signal, minus 4 times the synthesizer signal. The mid-2 is the LO signal. So the LO, the down-converted signal, the second harmonic. So this is really the second harmonic of the signal in here. It comes in because, and that's why this is really a lot of times when we're operating these, we chop it to bands, because in this case, for instance, you might want to operate just up to here. That's band 1, because obviously beyond that, your second harmonic will start coming into play. In this case, of course, it's minus 80 dBm down from minus, say, 20 So it's 60 dB down. It wouldn't matter really. And then it shows you other components as well. So you can go and see all of these things. So let's get back to this guy here and let's look at this. So like I said, okay, so right now the desired signal, the SATCOM signal, I'm sending it at minus 80 dBm. Okay, so at minus 80 dBm. So let me go back to this here. So I can come in here, and then as soon as you start hovering, you get basically you can see what this output signal in here, what had caused it, and you can actually draw a balloon on it, create a balloon. You can see that, and there you go. So you can see that right there. Okay, that's the mode that I was doing. Okay, so let's see the now this is again shown. You know, you can come in here at any particular point and start seeing the level of the signals in this ways. So also you can monitor the spectrum of the CW signals. Like for instance, this is the 10 gigahertz. So that's the 4 times frequency. Okay, so you can see the harmonics and spurs coming from the 4 times multiplier. Okay, from the synthesizer. Okay, all of these you want to make sure that you reject them with your filter. Okay, so that's about it. So again, now if you let's see, let's go back to the specification for one of these commercial devices. So 60 dB of gain, we have met that. Noise figure, we know we met that. We don't have the, it's the design right now doesn't have the waveguide to microstrip transition, but we've met 0.6 dB, so we have 0.2 dB as a budget left for the loss of the transition. The image rejection 40 dB, we met that. The output compression 15 dBm, we met that. Okay. And then the IP3, the output is always 10 dB, of course, above that theoretically. And we met that. So if you meet this, automatically this is met. Okay, ladies and gentlemen, so just a little announcement before I leave you until the next video. Like I said, I have my own training taking place here where I'm operating out of Georgia. My training is a 3-day training on the RF and microwave device and 3D modeling using HFSS. We could now, if you want to register to that, I do it at a local hotel here in the city. This is the YouTube channel videos. You can look at the material we cover on there. And this is my email. You can email me to get started on that. So I also have another training that is both done for the SystemVue, the kind of work like I just showed you, the LMB design. We sit down, we construct that from the beginning. You come in with an evaluation copy of the software installed on your laptop, and we construct all of these from ground up. You get the files from me for the whole thing. If you want to look at, browse around, see how things were done, but you yourself will learn how to use that tool and do actual real world designs. And then also I have an ADS one that just basically for the linear simulations and nonlinear simulations of circuit designs, microwave circuit designs. So until next time, I do thank you. I hope you enjoyed this. Please share this and click like and do whatever. Thank you very much, ladies and gentlemen. I appreciate it. We'll see you in the next video.